So I talked about how emission targets are set in international law, and I talked about the physical aspects of that. Now I'm going to talk about how an economist would look at this using cost-benefit analysis. I'm going to start with a recap of cost-benefit analysis. We talked about it last term. I'm going to talk a little bit about the orders of magnitude of marginal costs and marginal benefits. That's material we've seen in previous weeks. I'm going to talk about Northhouse's DICE model, and I'm going to talk about the fossil-free backstop and how that changes or not the calculus. So what you do in a cost-benefit analysis is essentially you set the marginal cost equal to the marginal benefits, and that's pretty straightforward if we have a static problem. So in brown you're looking at the marginal private gains from emissions, or rather from energy use, and at a certain point they go to zero, and that is where the unregulated equilibrium would be. And these marginal private gains fall for intuitive reasons. You stop heating your home because it is too warm in your apartment. You're not just keep heating and heating and heating because energy costs money, and at a certain point it just becomes uncomfortably hot. Similarly, at a certain point you're going to stop driving because you've reached your destination, because petrol is expensive and you don't want to waste your time driving around. So that is why that brown curve hits zero at some point, and that is how much you would emit if you would completely disregard the externality of your emissions. The green curve measures the benefit of emission reduction or the costs of unregulated emissions, and if there's no emissions they go for zero, and if there's emissions are high, those externalities are higher. And then the optimum lies where the marginal costs equal the marginal benefits, and that's the black line you're looking at. Different way of saying marginal cost should equal marginal benefits is saying, well, the marginal net gains, social gains, should equal zero, and that is the red line that you're looking at. So this is graphical. You can do the same thing symbolically. So we want to maximize net welfare, which is the benefits of your emissions minus the costs of your emissions, and this is an unconstrained optimum. So the marginal welfare should equal zero, so dW dE is the choice that we're making, emissions should equal zero, so that means that dB dE minus dC dE should equal zero, or marginal benefits dB dE should equal marginal cost dC dE. Now this is if you have a static problem. Of course climate change is a dynamic problem, and the way we typically think about this is that the benefits are a stock and the costs are a flow. That is, if we reduce emissions, then the costs of that emission reduction only depends on the actions we undertake in that particular year, while the benefits is avoided climate change, and that is something that accumulates over time. And in that representation of the problem, which is a decent approximation, not more than an approximation, but a decent approximation, in that particular representation, the marginal costs, because that's a flow, should equal the net present value of the marginal benefits, because that is a stock. Symbolically, what we want to do is maximize the net present welfare, which is the benefits B, which depends on emissions at the same time, emissions in the year before, emissions in the year before that, minus the costs of E, and as I said, we assume that that depends only on emissions in that particular year. And then of course this is in a present value, so we should discount the whole thing back to today by dividing by 1 plus r to the power t. And now we need to choose emissions E at every point in time. So it's not a single maximization problem, but it's a multiple maximization problem where we choose many emissions simultaneously. First order condition is that for every t, that's the weird thingy you see to your extreme right, for every t, the first order condition looks as follows. So dc dt, dct det for every t that is not equal to t, so dc des for every t, for every s that is not equal to t is 0. So what we have there is dc dct det. All the rest drops out of that sum, so that is relatively straightforward. Of course, we need the discount factor 1 over 1 plus r to the power t for that. So that is the right hand side of the first order condition, and the marginal costs at time t should equal the marginal benefits of time t, and that is a sum of how much your emissions at time t affect climate change, and the impacts of climate change at time t, but also at time t plus 1, and also at time t plus 2, and also at time t plus s, right? And it's the sum over all those things, of course, discounted to period t. So the discount factor there is 1 over 1 plus r to the power s plus t. Now we have 1 over 1 plus r to the power t on both sides of the equations. So that's essentially a constant in sort of the middle term you're looking at, so we can bring that in front of the summation sign, and then we can drop the 1 over 1 plus r to the power t. And what we have is that the marginal cost of emission reduction at time t should equal the marginal benefits, which is a stream of benefits from time t to the indefinite future, discounted to that particular point in time. Now structurally, nothing has changed. Marginal costs should equal marginal benefits. It's just that the marginal benefits have now become a net present value, but we're still in the same conceptual situation that the optimum is, where the marginal costs equal the marginal benefits. Now, we've seen marginal costs and marginal benefits before. What I showed you in week 3 was a table of carbon taxes corresponding to greenhouse gas concentrations in the year 2100. This is the same information, but now it is a graph. And what this says is, you can interpret this in two ways. Sort of the thick black line you see is the median of all the models that I showed you before, and then the thinner lines, the lighter lines, are confidence intervals around that, so that's an indication of model disagreement. Now there's two ways of reading this graph. One is if you want to achieve a target, say, of 550 parts per million, then you should impose a carbon tax in the year 2015, or should have imposed a carbon tax in the year 2015 of around $100 per ton of carbon. That is one way of reading this graph. The other way is reading it in the opposite direction and say, well, if I impose a carbon tax, or had I imposed a carbon tax of $100 per ton of C in the year 2015, then I would have been on track to reaching a target of 550 parts per million. So this is just a supply curve of climate policy, if you will. So we talked about this in week 3, and then in this must have been week 6, I talked about our the social cost of carbon, or our willingness to pay for climate policy at the margin, and that was fairly uncertain too. And here we see that displayed as a probability density function, And if we take the mode of the social cost of carbon, if we use 3% pure rate of time preference, a 5% discount rate, then our modal impact is around $27-28 per ton of carbon. Of course, if we impose this carbon tax and we reduce emissions, and it means that we take away part of the problem, so the BQ tax is slightly lower, but say around, in the mode, around $24 per ton of carbon. Now, if we go back to our supply curve, if we impose this particular carbon tax, then we're aiming for a target of perhaps 630 parts per million by the year 2100. So that is a very rough cost-benefit analysis. If we take the estimates of the social cost of carbon as given, when we impose this particular carbon tax, then we're heading towards 650 parts per million. Now, this is completely at odds with what the Paris Agreement wants us to do. The 2 degrees target, actually we should stay, we should aim at perhaps 500, perhaps a little bit less parts per million. The 1.5 degrees target, we should stay below 400 degrees. Or in different words, we should impose a carbon tax of well over $100 per ton of C, but maybe over $1,000 per ton of C. This is very, very far away from both our estimates of the social cost of carbon and current carbon prices around the world. So this is a very rough and ready cost-benefit analysis where we say marginal costs are this, we've seen estimates of that, marginal benefits, social cost of carbon are that, we've seen estimates of that. Let's just equate the two and see what happens. And what you see happen is something that is far, far away from what international law tells us. Now, as I said, that is a rough and ready cost-benefit analysis. Bill Northhouse of Yale, a recent Nobel laureate in economics, built what he called the dynamic integrated climate economy model, which is essentially a solo swan model of economic growth. You've seen that in macro. And he coupled that particular model to models of how the carbon cycle responds to emissions. Of course, he first had to extend the solo swan model to emissions, much as we have done in our exercises. And then he coupled that to a carbon cycle model, and you've seen that already, and he coupled that carbon cycle model to a model of climate change and the impacts of climate change. Basically what you've done in the computer labs so far is build this particular model, much like Northhouse did. Now, he won a Nobel Prize for this, so you won't. But that's basically what he's done. And the difference between the rough and ready cost-benefit analysis and the Northhouse DICE model is essentially that in the rough and ready one, we ignored a lot of feedbacks. But it turns out actually that those feedbacks do not really change the result. And Northhouse built this model to find an optimal climate policy, to do a cost-benefit analysis of climate policy. So I argued that the BQ tax should be around $25. Northhouse is slightly more aggressive, and he said no, we should start at 40, and then the carbon tax should slope up over time according to the schedule that you see here. If he imposes this particular carbon tax, then what happens is the following. So in black you're looking at Northhouse's reasonably arbitrary scenario without climate policy, and then in green you're looking at, given that particular scenario of business as usual emissions, what would happen if we impose this particular carbon tax. And what you see is that emissions fall. No surprise, we impose a carbon tax. What used to be free now, namely emissions into the atmosphere, are no longer free, and therefore we're going to improve energy efficiency, and we're going to find alternative fuels. so we reduce emissions, but what you also see is that emissions do not stabilize, right? By the end of the century, they're still rising, and they're nowhere near what would be needed for what is agreed internationally, right? So Northhouse's analysis violates first the United Nations Framework Convention, which says we should stabilize concentrations. That doesn't happen in this model, and it also doesn't come anywhere near what is needed to meet the Paris targets. So phrased differently, what did Northhouse do? And here you see his picture of a slightly younger Northhouse. I believe he's 78 at the moment. Northhouse essentially asked the question, if the world were ruled by a benevolent dictator, a philosopher queen, what would she do? And the answer that Northhouse gives comes in three parts, in green, red and blue. And Northhouse argues that we should do a little bit of emission reduction in the beginning, we should accelerate our efforts, but we should not do enough to stabilize concentrations. And the first part of Northhouse's conclusions is fairly robust. So when Northhouse wrote this for the first time, depending on what you take as his first paper on this, either in 1982 or in 1992, but it sort of first became prominent in 1992 with these conclusions. So when he wrote this in 1992, people got extremely upset. So what we have seen since then is that a great many people have tried to overturn Northhouse's conclusion. And I won't take you through all the perturbations there and all the different ways that people have taken his model and built alternative models and changed assumptions and so on and so forth, but I'll just give you the highlight. But people were extremely upset when he concluded this, and people have tried to overturn these conclusions. The first part of the Northhouse conclusion, that you should start slow and accelerate, that is extremely robust. And the reason that you should start slow is because a lot of emissions are essentially set in stone, and that means that the only way you can impose a very high carbon tax in the beginning, but that's not gonna change behavior. You're essentially punishing people for decisions they've made in the past. Unless, of course, the carbon tax is so high that you're going for large-scale capital destruction, and that's just too costly, right? So whatever you do, however you configure your model, you're always going to start slowly and accelerate. The fact that you're going to accelerate, or that you want to accelerate, that is very robust to however you configure your model. But how fast you want to accelerate is very sensitive to assumptions. So if you have a different discount rate, you would want to accelerate at a different pace. If you have different projections of the costs of renewables relative to fossil fuels, you would want to accelerate at a different rate. If you have a different representation of the carbon cycle, or a different representation of climate change or its impacts, you want to accelerate faster or slower than what Northhouse did. So he's robust in the sign, more later, but not at all robust in how fast is that pace. But then the bit that got people really annoyed is that Northhouse said, well, we should let climate change. We should not necessarily stabilize the climate. And that part of the conclusion, which flies in the face of basically everything an environmentalist would tell you about climate change, is the most contentious part of Northhouse's conclusion, and it's also extremely robust. And that goes back to the structure of climate policy. So what you do in climate policy is you equate the marginal cost to the marginal benefits. And you would almost always end up in some sort of inferior solution. So if you look at the structure of the marginal cost curve, a little bit of emission reduction is cheap. I said before that engineers reckon that roughly 30% of emissions of energy use and therefore emissions serve no useful purpose, and that means that you can cut them at very low cost. We know that it's very cheap by now to cut emissions in power generation, because solar and wind are now so cheap relative to coal and gas that they're almost competitive. So the first bit of emission reduction is cheap, right? So that brown curve indeed starts rising very, very slowly. After we have decarbonized the electricity sector, we should go after emissions in transport, where the technical alternatives don't look quite so attractive, but at least we know how to do it. If we're talking about CO2 emissions from aviation, we're not there yet, right? So at the moment solar planes exist, but they can fly a pilot and a suitcase, but not much more. You can't cram 300 passengers into a solar powered jet. That just doesn't work. We don't know how to do it. Similarly, biofuels, we can mix them in with kerosene, but we can't fly a plane on biofuels yet. And the reason for that is twofold. One, biofuels tend to have a lower energy density, that is, you need more fuel to fly the same distance, and that makes it just very expensive. But more importantly, those biofuels tend to have a lower freezing point. So if you fly kerosene and you go up to 10 kilometers in the air, then your kerosene is still liquid and everything works as it should. But if you have bioethanol, for instance, then it tends to freeze at 10 kilometers in the sky. And then it's no longer good as fuel. It's very good for your emissions and essentially go to zero. It's not so good for passenger safety because your plane would come crashing down. So for aviation we don't have a technical solution at this moment. May come in the future, may come this decade, may come next decade, but at the moment we don't really know how to solve it. And so then we're at more expensive parts of emission reduction, and then if you go to 100% emission reduction, and that is of course what is needed for stabilization. 100% emission reduction means that we go after the last niche application of fossil fuels. It's a bit unclear to me at the moment what would be the last resort of CO2 emissions. It may be something like space flight. You could say, well, we could do without space flight. And that is definitely true for space flight involving humans. Most of the things that humans do in outer space is for show. They don't do anything that is particularly useful, so we can do without that. But that argument forgets that there's a lot of satellites in space, and those satellites are quite useful, not only for the images that they send back of pollution and other things, but also for a lot of the communications that we currently run. And well, you can argue we have enough satellites, but a satellite has a lifetime of around 10 years and they need constant renewal, and at the moment we just don't know how to get rockets into space without emitting a lot of CO2. We just don't know how to do that. In some science fiction books you would read about it, but they are science fiction books at the moment. And that means that it's going to be costly to reduce emissions by 100%, because we know how to cut emissions by 10% or 30% or 50% at a reasonable cost, but we don't know how to get at the final bits of emissions. So that brown curve really is the shape that you're looking at. A little bit of emission reduction is cheap, but then it's gonna get more expensive and more and more and more expensive as emissions are pushed towards zero. The benefit curve also looks as it is shown here. So the initial avoidance of climate change is very valuable. If we let emissions rip, the world may warm by 6 degrees, it may warm by 8 degrees, it may warm by 10 degrees. If we cut emissions such that the world doesn't warm by 10 degrees but rather by 9 degrees, that is valuable. If we cut emissions such that the world doesn't warm by 6 degrees but rather by 5 degrees, that is still pretty valuable. But that is not what we are talking about. If emissions have to go to zero, then climate change is going to go from 4 degrees to 3 degrees, from 3 degrees to 2 degrees, from 2 degrees to 1 degree, and then it already becomes, is that really so valuable? But then we're not going to stop there. We're going to slow climate change from 2 degrees to 1 degree relative to today, right? And then from 1 degree to half a degree, and then from half a degree to 0.1 degree, and from 0.1 degree to 0.01 degree. And actually the natural climate variability without CO2 or anything is that the temperature goes up and down globally by 0.1 degree per decade. That's the natural variability, and we're going to stop climate change, so we're going to push it down from 0.1 degree, the natural variability, to 0.01 degree, which is actually the accuracy with which we can measure the global mean surface air temperature. And then we're going to push it down from there to zero. And it's very hard to imagine that at that point, when there's almost no climate change to start with, reducing it to no climate change would have any measurable or identifiable benefits. And that means that that green curve, yes, really goes through zero. It starts high, presumably, but it really goes through zero. Whereas that brown curve at that point where emissions are almost zero, yes, it's going to be very expensive to get rid of the final bit of CO2 emissions because there's no technical alternative. And that implies that however you're going to structure your cost-benefit analysis, you are always going to end up in a interior solution. And that means that yes, emissions should be abated, and that's what Northhouse found, but emissions should not be completely abated. They should not go to zero. They should be reduced from 100% as for what they would be without climate policy. But it's very hard to justify in a cost-benefit analysis that they should go to zero. And that is what Northhouse found, and that is what upset a great number of people. And people have tried to disagree with Northhouse, but nobody has credibly been able to do so. And there's one exception to this, and that is if there is a so-called backstop technology. I phrased that on the previous slide, unless there is a cheap alternative to fossil fuels. But if you introduce a carbon backstop into a Northhouse-like model, as Northhouse himself actually did, then that conclusion changes and you can stabilize the climate in a cost-benefit analysis. And that carbon-free backstop has to meet 4 criteria for it to be a backstop and work in this way. And the backstop technology is a term that I believe Alan Mann came up with. It's an energy source that we don't know what it is, but it doesn't emit any carbon, and it's some sort of futuristic technology that we invent. And that backstop technology has to meet 4 criteria. First, it's carbon free, it does not emit CO2. And we have a number of alternatives there. Solar, wind, biofuels do not emit CO2, nuclear, hydro. So yes, that criterion is easily met. We know that these things exist. Second criterion is that this backstop energy becomes competitive with fossil fuels if we impose a carbon tax, a finite carbon tax on those fossil fuels. Again, this is not a stringent condition. Wind, solar, biofuels meet this condition already. So this is not futuristic at all. The third criterion is that this backstop technology, this backstop energy, isn't just competitive at the margin, but it's still competitive when it has completely replaced fossil fuels. It's also competitive at market saturation. And that is a much tougher condition to meet. So yes, at the moment it looks as if in a few years' time offshore wind in the North Sea will compete with gas-fired electricity generation at the margin. If that, and the same is true for land-based wind power in the Texas Panhandle. At the moment it competes with gas at the margin. That is not to say that we can completely replace all our gas-fired power plants with wind turbines, because wind is unreliable, it's unpredictable. Sometimes the wind just doesn't blow, so we need more backup capacity. Wind is typically, you can't say where the wind should be, and a lot of the good winds are far away from where the people are, whereas a gas-fired power plant you can't just place where you want it to be, so transportation costs are higher and so on and so forth. And that means that even though for an existing system, if you want to build a new power source, if you want to add a new source of electricity to the system, then by the year 2030 you would actually be crazy if it would not be wind or solar. But that is an additional source of electricity. Replacing all fossil fuels, all gas and all coal with wind and solar is actually going to be a lot more expensive for the reasons that I just gave you, but also because the good spots for wind and the good spots for solar will be crowded with wind turbines and solar panels, and you would need to move to places where the wind doesn't blow that strongly, or the wind or the sun doesn't shine that hard. That means that your costs of these sources of electricity will go up, right? So the third criterion here, the third condition that a carbon-free backstop has to meet, is much more difficult, and at the moment seems to be infeasible, but then again give it a couple of decades and those conditions may be completely changed. But then there is a fourth condition that a carbon-free backstop has to meet in order to change the cost-benefit calculus, and that I find very hard to imagine. And that is actually at this particular point in time is easy to illustrate. And that is that once this carbon-free backstop has taken over the energy system, there is no looking back. You would never would never go back to fossil fuels. This is so-called hysteretic. Of course, if this carbon-free backstop takes over the energy system, then CO2 emissions go to zero, and that means that your climate problem goes away. And that means that there's no justification for a carbon tax anymore. So the carbon tax is eventually going to go to zero. But at that point, when the carbon tax goes to zero, you don't want to go back to your fossil fuels. And that means that your carbon-free energy source has to compete on its own merits with fossil fuels. And that is a very tough condition to meet. Because if we drive out all fossil fuels prematurely, so that it actually makes a real dent on your climate, that means that there's still oil in the ground in Saudi Arabia. And well, you can imagine that biofuels compete with petrol and diesel when the price of a barrel of oil is $50 or $70 and the price of a ton of carbon, or the carbon tax or the carbon permit, is $50 or $100 per ton of carbon. At those prices, you can imagine that biofuels compete with petrol and diesel. But the price or the cost of getting a barrel of oil out of the soil in Saudi Arabia is $4 a barrel. And if the oil price drops from where it was 50 to where it is now 20 or so, the carbon tax needs to be really, really, really high in order to make biofuels competitive. And similarly, if we're going to decarbonize the power sector, we're going to leave a lot of coal in the ground. We're going to leave a lot of coal in the ground that is cheap to get out and easy to burn. And it is very hard to imagine that if the carbon price drops to zero, then nobody will get it into their heads to start digging for coal again, or to start pumping for oil again. Because those resources will be very cheap, and we have all the technology that we need to get them out of the ground and burn them. So this last condition, that we will never look back, is actually, I believe, the most unrealistic assumption that goes into a carbon-free backstop. If you're prepared to make these assumptions, then yes, in a Northhouse type model, climate stabilizes. Northhouse is prepared to make those assumptions. I am not. But if you are, then yes, your climate would stabilize also in the cost-benefit analysis. Not necessarily at the levels that the Paris Agreement prescribes, but it would definitely happen. Now, what we're going to do next week is take a closer look at what Northhouse really assumed, and particularly look at the definition of what do we actually consider optimal, and that changes not these particular conclusions, but does change at what level you would want to reduce your emissions. And then the week after, we're going to look at, because Northhouse essentially assumed that the whole world was ruled by a benevolent dictator, a philosopher queen, but that's of course not realistic. What would happen if there's many countries, and what we'll find, what we expect, is that optimal emission reduction goes down if there's many countries. But before we go do that, we are going to look at what happens if climate policy does not just affect climate change, but affects other environmental problems as well.